Welcome to my 29th tutoring session in A-level chemistry. In this video, I'll talk about atomic radius and give a detailed explanation about covalent, metallic, ionic and van der Waals radii. Please take a moment to watch my previous videos on topics chemical bonding and types of chemical bonding, as these videos will provide you with a better understanding of this video content. Link to the videos given in the description below. Please do watch the videos. Don't forget to subscribe my channel, share, like, comment and watch the full video. What is atomic radius? Now, atomic radius refers to the size of an atom, specifically the distance from the nucleus of an atom to the outermost electron shell in a neutral atom. Now, you cannot determine the atomic radius directly by measuring the distance between the nucleus and the outermost electron shell. The reason is the atom lacks a sharp and well-defined boundary of the electron cloud. And as we all know, electron is always in constant motion and orbits around the nucleus in their respective shells or energy levels. So it is very difficult to locate the exact position of the electron in an atom. And another important reason being the wave-like behavior of an electron in an atom. So it is not only in constant motion, but also it has a wave-like behavior in an atom. Now here's a scenario where you got 4 different positions of the same electron. Now these are not 4 different electrons, these 4 are the same electrons but at different positions. So the position of an electron keeps on changing as the electron is in constant motion, and also it has a wave-like behavior. So as a result, these are the 4 different positions of the same electron. And when you try and measure the atomic radius for these 4 different positions of the same electron, you will end up with 4 different atomic radii. So how do you approach this problem? So how to go about this problem? So the only solution to this problem is to measure the radius of an atom when it is in the bonded form. That is when the atom is held together by a covalent metallic or ionic bond. So you can determine the radius of an atom in the bonded form. That is when the atom is bonded to another atom by either covalent metallic or ionic bond. So let me explain the measurement of metallic radii with respect to magnesium atom. In the crystal lattice structure of magnesium metal, you will find the magnesium atoms closely packed to each other, and because of this close packing, you will see these magnesium atoms as closely touching spheres or circles. So in the crystal lattice of magnesium metal, you can find the magnesium atoms, or it can be seen as touching spheres or touching circles. So they are in close contact with each other because of the close packing. So you can find the internuclear distance. So the internuclear distance for the magnesium between the two magnesium metal atoms is 320 picometers. So you take an average value and that will give the metallic radius. So 160 picometers is the metallic radius of magnesium atom in the crystal lattice structure of magnesium metal. So metallic radius is defined as half the distance between the nuclei of two adjacent atoms in a metallic lattice, and it represents the size of metal atoms in a metallic solid where the atoms are closely packed together in a crystal lattice structure. So the internucleus distance between two magnesium atoms in a metallic lattice of magnesium metal is 320 picometers, and the atomic metallic radius in picometers of magnesium atom is 160 picometers. So when you take average of 320, when you divide it by 2, you get the value of 160 picometers. So 160 picometer is the metallic radius of magnesium atom. So the concept of atomic radius is crucial in understanding the properties and behaviors of atoms and elements. An atomic radius is measured in picometers, and 1 picometer is equivalent to 10 to the power of minus 12 meters. So now you have an idea how to determine the radius of an atom. So there are different types of atomic radii, each describing the different aspects of the size of an atom. And the method used for determining the radius of an atom, it depends entirely on the type of the bond that holds the atoms together. So it could be a covalent bond, metallic bond, ionic bond, or even van der Waals forces holding the atoms together. So a covalent radius can be determined for atoms that are held together by covalent bond. Now covalent bond, as you all know, is formed by mutual sharing of electrons between the atoms involved in bond formation. So a covalent bond is formed by mutual sharing of electrons between atoms involved in the covalent bond formation. So the probability of finding the shared pair of bonding valence electrons is halfway between the two nuclei. So here the electron boundary is fixed to some extent. So after the covalent bond is formed between the two atoms, the electron boundary is fixed because the sharing pair of bonding valence electrons is halfway between the two nuclei. Or you can say the electron density is more between the two nuclei, or between the two bonded atoms. So a covalent bond is formed between two atoms by mutual sharing of electrons, and this is shown by a solid line joining the two atoms. For example, so in case of hydrogen molecule, a covalent bond is formed, and that is shown by a solid line joining the two hydrogen atoms held together by covalent bond. Now you calculate the internuclear distance between the two nucleus and take the average. So the internuclear distance for hydrogen molecule is 74 picometers. You take the average, divide by 2, and 37 picometers is the covalent radius of hydrogen atom. So the electron boundary is fixed when the atoms are held together by a covalent bond. That is to say, the electron density or the electron cloud is halfway between the two nuclei. So only when the electron boundary is well defined, you can determine the radius of the atom. And metallic radius is determined for metal atoms held together by metallic bond. Now in the crystal lattice structure of a metal, you will find the metal atoms are closely packed to each other. So there is close packing of metal atoms in a solid metal, and they are seen as closely touching circles or spheres. So you can measure the internuclear distance and take the average. So the internuclear distance for magnesium is 360 picometers. You take the average, divide by 2, and you end up with the metallic radius. So 160 picometers is the metallic radius of magnesium solid metal. And ionic radius is determined for ions held together by an ionic bond. Now this is a different scenario altogether because the cations are smaller than the anions. Or you can put the other way around. The anions are larger in size as compared to the cations. Because during the bond formation, the metal atom loses its electrons and loses its outmost electron cloud. And while the non-metal gains the electrons and becomes negatively charged. It increases in size because of interelectronic repulsion in the respective shells. So the ionic radii of the cation is always smaller than the ionic radii of anion. So ionic radii of sodium ion is 102 picometers, while the ionic radii in case of chloride is 181 picometers. So first you have to calculate the internuclear distance between the two ions and then calculate the ionic radii either for the cation or for the anion. So first calculate the internuclear distance and then find out the ionic radii either for the cation or anion. So when you know the ionic radii for cation, you can find the ionic radii for the anion. If you know the ionic radii for anion, you can always calculate the ionic radii for cation. So ionic radii for sodium ion is 102 picometers, chloride ion is 181 picometers, and the internuclear distance will be sum of these two. So here in this case, you cannot take the average. If you take the average of these two ionic radii, you'll get a bigger value. You'll end up with wrong ionic radii. So never take the average because the size of the cation is smaller than the size of the anion. And the van der Waals radius is specifically used for non-bonded atoms and non-polar molecules that are held together by van der Waals forces. For example, in case of monoatomic noble gas helium, atomic number is 2. There are 2 protons in the nucleus of helium atom and 2 valence electrons. And there is a neighboring helium atom. And both the helium atoms come close together because of van der Waals force of attraction. And they tend to repel beyond a particular point because of internuclear and interelectronic repulsion. And van der Waals radii will be the half the distance between the nucleus of 2 non-bonded helium atoms. So what kind of information can we expect from calculating the atomic radius of the atoms held together by covalent, metallic, ionic or van der Waals forces? Now these different types of atomic radii, they provide valuable insights into the size and bonding behavior of atoms in different chemical environments. Now these different types of atomic radii, they provide valuable information about the size of atoms and ions and are used in various areas of chemistry, including understanding various chemical properties and behaviors of elements. And they are also useful in determining the molecular geometries, predicting the bond lengths and understanding trends in the periodic table. Now let me explain all these 4 radii with suitable examples. Let me start with the covalent radius. Now the covalent radius is a measure specifically used for atoms bound in covalent compounds. So radius of an atom can be determined for compounds held together by covalent bond. So what are covalent compounds? Now covalent compounds are those compounds where the atoms are held together by covalent bonds. That is a bond formed by mutual sharing of electrons. So here we got atom A and atom B. This is the nucleus of atom A. This is the nuclear proton of atom B. Valence electron of atom B, valence electron of atom A. And there is electrostatic force of attraction between the valence electron of atom A to that of the nuclear proton of atom B. And you also find electrostatic force of attraction between the valence electron of atom B and nuclear proton of atom A. So as a result of this mutual attraction between the nuclear protons and valence electrons, both the atoms come close together because of the mutual attraction, and there will come a point where the electron pairs are equally shared, resulting in formation of a covalent bond that is shown by a solid line between the atoms held together. That part of the covalent bond. So here, for example, the two hydrogen atoms, they come close together. A covalent bond is formed between them by mutual sharing of electron pair. So the probability of finding the shared pair of bonding valence electrons between the two nuclei is more. That is to say, the electron density is more between the nuclei of two hydrogen atoms. So overlapping of the two electron clouds result in formation of a covalent bond, or you can put it the other way around. Overlapping of atomic orbitals of the two hydrogen atoms, this is in formation of the hydrogen molecule. So after the mutual sharing of electron pair, the electron boundary is well defined, and therefore you can take the measurement of the distance between the nuclear protons. And same explanation holds good even for fluorine molecule. A fluorine molecule is formed by mutual sharing of electrons between two fluorine atoms, and the covalent bond formed between the two fluorine atoms is shown by a solid line joining the two fluorine atoms. So in case of fluorine molecule, a covalent bond is formed. So the electron density is more between the two nuclei. So the shared pair of bonding valence electrons is halfway between the two nuclei, and therefore you can measure the internuclear distance and take the average. So 144 picometers is the internuclear distance for fluorine molecule. And when you take an average, divide by 2, you'll get value of 72 picometers. So the internuclear distance between the two fluorine atoms in a fluorine molecule is 144 picometers, and the atomic radius in picometers of fluorine atom is 72 picometers. That is 144 divided by 2, you get 72 picometers. And same explanation holds good even for the hydrogen molecule. So hydrogen molecule is formed by mutual sharing of electron pair between the two hydrogen atoms. So the internuclear distance between the two hydrogen atoms in hydrogen molecule is 74 picometers, and the atomic radius will be average of the atomic radius in picometers of hydrogen atom is 74 divided by 2, that is 37 picometers. So the covalent radius is defined as half the distance between the nuclei of two identical atoms when they are covalently bonded in a molecule. It is typically used for atoms bonded in covalent compounds. For example, in a hydrogen molecule, the covalent radius of each hydrogen atom is half the distance between the nuclei of the two hydrogen atoms in the molecule. And in case of fluorine molecule, the covalent radius of each fluorine atom is half the distance between the nuclei of the two fluorine atoms in the fluorine molecule. Now, the concept of covalent radius is crucial for understanding the characteristics of atoms within covalent compounds. Now, metallic radius specifically applies to metal atoms which are closely packed together in a crystal lattice structure. Let me explain the concept of metallic radius with respect to the sodium atom. So what you see here is the electronic structure of sodium atom in the zero oxidation state, that is in the unreacted form. A sodium atom, it has total of 11 protons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, and only valence electron in the outermost third shell. That is a valence shell. Now the valence electron is loosely held and free to move around. So electronic configuration of sodium is 281, 2 electrons in the first shell, 8 electrons in the second shell, and only valence electron in the outermost valence shell, that is the third shell. So this is a symbolic representation of sodium atom with freely moving valence electron, outermost valence electron. So the valence electron is present in the 3s orbital, present in the third energy level. So electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. And it's also represented by numerical notation 281 or by a condensed electronic configuration using the previous noble gas, that is neon, which is mentioned within the parenthesis, followed by the only electron in the 3s orbital, that is 3s1. Now here you find the 4 metal atoms, sodium metal atoms, and these sodium metal atoms experience a strong electrostatic force of attraction between them. And the reason for the electrostatic force of attraction between them is the nuclear protons, that is 11 protons present in the nucleus of sodium atom and the only valence electron present in the outermost shell. So as a result of the strong electrostatic force of attraction between the nuclear protons and the loosely held valence electron, the metal atoms, they come close together and this leads to close packing, and a network is formed between the sodium metal atoms. So here you see a close packing of the sodium metal atoms in the crystal lattice structure of sodium metal, and this because of delocalized sharing of negatively charged electrons among the sodium metal atoms. And there is a strong electrostatic force of attraction between the positively charged metal atoms and the negatively charged loosely held delocalized valence electron. So a metallic bonding occurs between metal atoms in a solid metal. So here we are talking about the sodium metal. In a metal crystal, atoms are arranged as touching circles with the distance between nuclei of adjacent atoms being precisely twice the metallic radius. So in the crystal lattice structure of sodium metal, you will find the sodium atoms as touching circles or touching spheres. So sodium metal atoms are seen as touching spheres or touching circles in the crystal lattice structure. So you calculate the internuclear distance between the two metal atoms, and the internuclear distance for the two metal atoms is 320 picometers for the magnesium atom. That is between the two magnesium atoms in the crystal lattice structure of magnesium. So metallic radius will be the average value. So divide 320 by 2, you'll end up with 160 picometers. So the metallic radius is defined as half the distance between the nuclei of two adjacent atoms in a metal lattice, and it represents the size of metal atoms in a metallic solid, where the atoms are closely packed together in a crystal lattice structure. Now moving on to the ionic radius. Now ionic radius specifically apply to ionic compounds where the cations and anions are held together by a strong electrostatic force of attraction. So in ionic compounds, you find the positively charged cations and the negatively charged anions held together by strong coulombic force of attraction, resulting in an ionic bond. So let me explain the concept of ionic radius with respect to sodium metal, sodium atom and chlorine atom. So what you see is the electronic structure of sodium atom in the zero oxidation state or in the unreacted form, and the electronic structure of chlorine atom in the zero oxidation state or in the unreacted form. Now sodium is a metal while chlorine is a non-metal. Now sodium is a metal and therefore it tends to lose electrons because of low ionization energy, and chlorine being a non-metal, it tends to accept electron given by the sodium atom because of its high electron affinity. So sodium loses electron because of low ionization energy, and chlorine atom accepts electron because of high electron affinity. So sodium is a metal with low ionization energy and chlorine is a non-metal with high electron affinity. And this results in formation of sodium ion and chloride ion. Now when you compare and contrast the size of sodium ion to that of chloride ion, you will find the size of sodium ion to be smaller and the size of chloride ion to be larger. The reason is the sodium atom, after losing its outermost valence electron, it has lost its outermost valence shell and therefore shrinks in size, and in the process gains a positive charge, while the chlorine atom, because of its high electron affinity, accepts the electron given by sodium atom and forms a negatively charged chloride ion. So after accepting the electron by the chlorine atom, it leads to inter-electronic repulsion between the electrons, and that leads to the spreading of charges, and this leads to occupation of more space. The electron cloud expands because of inter-electronic repulsion, and as a result, the anion, in this case the chloride ion, is bigger in size. So one more important reason why sodium atom loses electron while the chlorine atom accepts an electron is because both sodium and chlorine, they want to attain the stable electronic configuration. So the driving force for the sodium to lose electron is to attain the stable electronic configuration of neon, and the driving force for the chlorine to accept electron is to attain the stable electronic configuration of argon. Now the electronic configuration of sodium before losing electron is 281, and after losing its only valence electron, sodium has attained, or you can say sodium ion has attained the stable electronic configuration of neon, which is the nearest noble gas in the periodic table. And what about chlorine? Now chlorine atom, before accepting the electron, its electronic configuration is 287. After accepting the electron, it has attained the stable electronic configuration of argon, that is 288. So argon is the only noble gas in the periodic table that is nearest to chlorine atom. Now metals tend to form positive oxidation states, while non-metals tends to form negative oxidation state. The sodium atom, after losing electron, it has taken a positive oxidation state of +1, and chlorine, being a non-metal, after accepting an electron because of high electron affinity, it has taken an electron oxidation state of, it has taken negative oxidation state of -1. So now we know why sodium ion is smaller in size while chloride ion is larger in size. So in case of ions, the cation will always be smaller than the anion in that particular ionic compound. So first you have to calculate or measure the internuclear distance. And after calculating the internuclear distance, you have to measure the ionic radii of cation separately and ionic radii of anion separately. So the internuclear distance for sodium chloride salt is, that is the internuclear distance between the sodium ion and chloride ion is 283 picometers. And ionic radii of sodium ion is 102 picometers. And ionic radii of chloride ion is 181 picometers. So now you know the internuclear distance and the ionic radii. So you should know the internuclear distance and the ionic radii of either cation or anion. If you know the ionic radii of cation, you can always calculate the ionic radii of anion. And if you know the ionic radii of anion, you can always calculate the ionic radii of cation, provided you know the internuclear distance. So the ionic radius is the size of an ion, typically measured as the distance from the nucleus to the outermost electron shell. It can vary depending on whether the ion is positively or negatively charged. For example, the ionic radius of sodium ion is smaller than that of a neutral sodium atom, while the ionic radius of a chloride ion is larger than that of a neutral chlorine atom. So why it is so? I've already explained in detail the reasons for the sodium ion being smaller than the chloride ion, or the chloride ion being larger than the sodium ion. Now moving on to the van der Waals radii. Now van der Waals radii are specifically used for non-bonded atoms like monoatomic noble gases and non-polar molecules such as diatomic halogens, which are held together by van der Waals forces. Now let me explain the concept of van der Waals radii with respect to the monoatomic noble gas helium and non-polar diatomic molecule, that is fluoride. Now helium, atomic number is 2 with 2 protons in its nucleus. There is a neighboring helium atom with 2 protons in its nucleus. So in a neutral atom, always the number of protons will be equal to the number of electrons. So you find 2 valence electrons in the first shell of helium atom, and these 2 helium atoms, they come close together because of electrostatic force of attraction between the nuclear protons of one atom and the valence electron of another atom. So there are 3 different scenarios. Scenario 1, the nuclear protons of helium atom 1 attracts the valence electrons of helium atom 2. And as a result of attraction, the 2 atoms come close together. Now second scenario, the valence electrons of the helium atom 1 repels the valence electrons of helium atom 2. So there is repulsion. This is scenario 2. What about scenario 3? Now in scenario 3, nuclear protons of helium atom 1 repulse the nuclear protons of helium atom 2. So there is repulsion. So there are 3 scenarios. 1 attractive force and 2 repulsive forces. So it is the attractive force which brings the 2 helium atoms close together, and it is the 2 repulsive forces which stops the helium atoms from further approaching each other. So the van der Waals radius will be half the distance between the nuclei of 2 non-bonded helium atoms when they are in contact with each other. And same explanation holds good even in case of fluorine molecules. So here you find 2 fluorine molecules. They come close together because of electrostatic force of attraction between the nuclear protons of one molecule and the valence electron of the another molecule. And the van der Waals radii in case of these 2 fluorine molecules approaching each other, that is when they are in close contact, will be half the distance between the nuclei of 2 non-bonded fluorine atoms of 2 neighboring fluorine molecules when they are in close contact. Now remember, in case of van der Waals radii, you are measuring half the distance between the nuclei of 2 non-bonded atoms. So there is no bond between the 2 helium atoms or the 2 fluorine molecules. There is absolutely no bond between the 2 helium atoms and the 2 fluorine molecules. So the 2 helium atoms or 2 fluorine molecules will repel each other beyond this point. So you may ask me, what happens if the 2 helium atoms come close together beyond this point? If they come beyond this point, if they approach close to each other beyond this point, they will repel each other due to interelectronic and internuclear repulsion. And same explanation holds good even for the 2 fluorine molecules. So the van der Waals radius is defined as half the distance between the nuclei of 2 non-bonded atoms of the same element when they are in contact with each other. And it represents the size of the atom when it is not bonded to another atom, but is in close proximity due to van der Waals forces. So it is the van der Waals force of attraction which is bringing the 2 non-bond atoms and non-polar molecules closer to each other. So I explained the van der Waals radii concept with respect to helium atom and the non-polar fluorine molecule. So for example, a noble gas atom's van der Waals radii represents the average distance between the nuclei of 2 noble gas atoms when they are in contact but not bonded. So remember, van der Waals radii are specifically used for non-bond atoms or non-polar molecules, and they are held together only by intermolecular forces, that is van der Waals forces. So let me give you one more example for the van der Waals force of attraction between the 2 noble gas, that is neon gas. So the 2 neon atoms, beyond a particular point, they will repel each other. So here you can see the 2 neon atoms approaching each other, and beyond a particular point, they will not come close together, because if they come closer, they will repel each other, and they will repel each other because of internuclear repulsion and interelectronic repulsion. So the 2 non-bonded neon atoms, they come close together because of attraction between the nuclear protons and valence electrons, and beyond a particular point, they will repel each other because of internuclear repulsion and interelectronic repulsion. And van der Waals radii will be half the distance between the nuclei of 2 neon atoms that are not bonded. So the 2 neon atoms will repel each other beyond this point due to interelectronic and internuclear repulsion. Van der Waals radius is half the distance between the nuclei of the neighboring non-bonded neon atoms when they are in close contact. So in summary, the van der Waals radius of neon represents the effective size of a neon atom, accounting for the space occupied by its electron cloud. It is a measure of the average distance between the nuclei of neighboring non-bonded neon atoms when they are in close contact. And it reflects the compact electronic configuration and non-reactive nature of neon. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.